We then address the question, what if the response is not linear? We made ground by recalling that the laser beam or the light, electromagnetic wave in general, polarizes the medium, that is, it creates, it leads to a net P of t. Okay. The P of t, so far we have assumed, oscillates only at omega, the frequency of the driver, right. We will soon need to throw away this limitation, right, which we need to do if particularly this motion is not sinusoidal. We looked at an acoustic example where amplifiers distort the input owing to their limited ability to amplify, but in terms of nonlinear optics, this essentially means that we can lead, this can lead us to fascinating phenomena where infrared light, okay, at about a wavelength of about 1 micrometer turns into green, which is one of the first demonstrations of this phenomena. And all this happens because the electron cloud, which is trapped in the 1 over r potential about the nucleus, gets driven into anharmonic regions of the electron potential, okay, electronic potential. For small displacements, just as in the case of the simple pendulum, we could restrict the response of this system to being harmonic, whereas when the response is, when the excursion of the electron cloud exceeds a certain limit, we are forced to include the not just the harmonic potential, but also quartic terms in the case of even order terms in terms of the atomic response. Excuse me. So, excuse me, I mean, this could be a good point to take a little break. If we are to, if you have any questions or any points of discussion to bring up, anything from the class, in person or online. Okay, I need a 30-second pause to have a sip of water. Okay, let us resume. So, we can essentially have processes where the emitted photon need not have the same energy as that of the incident photon, or the emitted frequency need not have the same as the incident frequency. Why do we need to consider that? So, if we consider excursions of the electron cloud to nonlinear regions of the potential, right, where force, this is not potential on the y axis, so vertical axis, that is, so please watch out, where force essentially is no longer a linear function of displacement, or potential is no longer just a quadratic function, a parabolic function of the displacement, then a larger excursion would mean sampling regions where nonlinear behavior manifests more strongly. Okay. So, if the electric field applied is sinusoidal, the total polarization, which is the response of the medium, need not actually even be symmetric about the 0 value for polarization. Okay. Polarization, after all, is an oscillating vector field. We could have a distortion as compared to the incident sinusoid. If this happens, then naturally we can Fourier decompose the polarization into oscillations at the fundamental frequency, at the second harmonic, and if need be harmonics of higher order 3, 4 and so on, plus we may need to also add a DC polarization at 0 frequency. Okay. So, all these will become a consequence of the nonlinear response of the medium. Okay. Input wave at one frequency, emitted wave at a new frequency or color, therefore, is not unforeseeable. So, the this opens doors to what we call nonlinear optics, that is linearity between the incident field and material response is no longer a given. Why? It is not a given if or when xc of t, which is the relative displacement between the electron cloud and the positive center, is large compared to what? Large compared to the regions for harmonic response, right. So, we want to qualify nonlinear of nonlinear optics, that is what is nonlinear in nonlinear optics. This depends on two factors, okay. An amplitude factor which depends on omega and omega naught, of course gamma 2, as well as the driving field E of t, okay. Atomic frequency response as well as amplitude of the driving field. So, what we looked for is xc being large, right. So, always as physicists, we scientists, engineers, whatever we like to call ourselves, we do not ask the question how large or how small, right. Maybe even in an economic context, but we are bothered always about is large or large, small. Compared to what, right, or the paradigmatic statement how small is small or how large is large. Okay. Essentially, we want to set the scale for this problem. So, here speaking in terms of the displacement of the atomic centers of charge, positive and negative, here in terms of displacement, if the region of harmonic response defines the large or small. You exceed this, you think we then start saying the displacement is large. You confine to this region, then the response is small. So, we have likewise the notion of small oscillations, is not it? Small oscillations linear or harmonic response, right. Small oscillations, we also say small oscillations and harmonic oscillator always together, right. Likewise, in electrical engineering, we have small signal response. Small signal is synonymous with linear, right. So, maybe we could write it like that. Small oscillations, harmonic oscillator, small signal, linearity, right. Both of these connote linearity. So, this indeed, the fact that we have small signal responses also tells us that we can not only compare the displacement of the driver to regions of perturbation of the system, we can also compare the strength of the driver, in this case the driver's E field, the driver's strength, that is in this case the E field of the driver. We can now compare this to something native inside the atom, right. What should we compare the driver's strength to? I maybe this is a question I must pose to the class. In terms of displacements, which are the effect of driving, we said that the displacement should be small compared to these regions where I can conveniently use a harmonic potential or a harmonic response of the medium to the driver. So, here if I have a field which has a certain strength, how do I measure the strength of the field? It is simply the magnitude of the electric field, right, which we measure in volts per meter. SI units are volts per meter, isn't it? So, then how do I qualify a driver to be a strong or a weak driver? How strong is strong, how weak is weak? Yes, but that is the consequence. The cause, in terms of the causal factors, this is caused, coming to that in a minute, this is caused by an electric field that a driving oscillating source of electric field, say a laser emits, and that radiation is incident on the matter. So, that field has a strength. I now want to compare this field strength to something, this is a characteristic of the light. I want to compare this to a characteristic of the material part, the atom. So, what? Yeah, the spring constant. But what does that, what spring constant are we then talking about? Where is the spring, where is the constant? Internal electric field in the atom. Yes, Pratik? Dissociation. So, Pratik thinks it could be the energy required to break the bond or the spring. Okay, something like the tensile strength of the spring. Suman thinks that it is the internal E field in the atom. So, can we determine the internal electric field in the atom? Actually, these two are kind of related. Excitation? Abhishek thinks it has something to do with the excitation energy. What excitation? Excitation energy of the electron, is that a unique number or what do we do? Of course.
Like how comparable is that to the field of the, how comparable is the field of the electric field to the energy?
How comparable is this to the electric field? What did you mean by that? Okay, now the electric field of the driver, if I take the absolute value square of this will give me a certain power density, that is the density of electromagnetic energy in the wave. I could compare this energy density with the energy required to break the bond or cause an excitation in the atomic system. I can compare this field energy to this and say, okay, if you now have enough energy, then something can happen, right? But this is where we should be a little careful. Why should we be a little careful? The energy density of the field can be increased by increasing the amplitude of the incident electric field, right. Of course, this oscillates, so I am sketching only one half of the field amplitude. So, is increasing the strength of the electric field going to lead to a dissociation, or in this case the emission of an electron, or the photo emission of an electron from an atom primarily? What does it critically depend on? Does it critically depend on the increase of the field amplitude or the frequency of the field? It's a little bit of an irony, right? It's counterintuitive, don't you think, that we have to associate the frequency of oscillation with respect to the removal of the electron from or breaking this bond. Quite naturally, as Abhishek said, we would have imagined in this picture where the electron is simply making excursions about about the zero displacement position, that if I, and since as I've basically pointed out here, this excursion depends upon directly on the field amplitude. So, if I remove the electron far enough, I must have at some point broken it away from its parent atom, right. So, it must depend systematically on the amplitude of the input field, it seems. But strangely, that nature does not seem to think that way and work that way, right. It seems to work more by the notion, which also a parallel conceptual notion which we introduced earlier, did we not? We said that for resonant oscillations, omega nearly equal to omega naught, the natural driver, magically the amplitude of the oscillation in response to the driven field is many times over, right, because we have an omega square minus omega naught square term, because the amplitude depended as 1 over omega square minus omega naught square, right. This really made things go through the roof. This way of increasing the amplitude, it seems, is more important than this way of increasing the amplitude of oscillation. This kicks in non-linear, in some sense this breaks the response from being linear, close to the what we call the resonance, and something dramatic happens when omega hits omega naught. That is the message. So, that dramatic response is either a very nice absorption and the system changing its state. Okay, we can even see this in a classical response of the system, okay, or the system even breaking apart, okay, which is not so obvious from everything. It should not be, because that is where we needed to introduce the notion of a quantum of electromagnetic radiation or light. The notion of light quanta essentially emerges from this. So, up to this thing, we can envision the fact that the field strengths are not solely responsible for the bond breaking aspect. So, I will therefore take the liberty of erasing this out and saying that the two things therefore to be compared with are not so much in the domain of energetics, that I compare the energy density of the incident radiation and that of an inherent energy, which could be frequency times a constant like the Planck's constant. What instead we want to make a direct apples to apples comparison is the native field inside the atom, okay, and that of the driver. In fact, for a multi-electron system, the native electric field can also depend upon the most probable location or to find the electron inside an atomic or molecular system, right. So, we can call this the the Kepler radius of an orbital. Although this picture of an orbiting electron is wrong, so we should question the use of such a notion or notation. Let me make this big. Nonetheless, that is why we call this the Kepler radius, because it is the radius of an equivalent planetary like system. Not the true picture. Nonetheless, an A for this distance and a Z for the charge held by the nucleus, or since we are considering a single electron, okay, in this case the charge of the nucleus is often screened by some intermediate electrons which are present over here, right. So, can model this in many different scenarios and ways, but an effective charge that is visible to this electron at this location A along the radial coordinate system, right, and a fictitious Keplerian path for the trajectory which does not exist as per quantum mechanics, but then we can consider this to be a multitude of trajectories, which we do not know exactly about, but then on an average you can figure out the most probable value for the radial coordinate where you can detect the electron using a fictitious point detector which if it was placed there. We have solved this problem in the case of hydrogen atom, right. Remember that you must have calculated mod psi square, and then this is again one more p in this picture unfortunately, right, and taken the radial function at least and then calculated a radial probability density, and we must have done this exercise of r is equal to r max where this went to a 0. Right. We must have done this in some position which is the value that corresponds to the Bohr radius of the hydrogen atom. So, we can place the electron on an equivalent Keplerian path around the nucleus, because the electron also remember has a velocity v whose expectation value is computable from in quantum mechanics. It is an observable, legal observable. So, all this lends itself to such a simplistic effective model for the atom. So, then this gives us the opportunity now to compute the electric field experienced by this single electron even in a multi-electron atom, because we are living in this scenario where in all this formulation we have considered the response of a single electron to the electromagnetic field for ease and for the sake of keeping things manageable over here. If we do not do this, we run into another level of complexity which we are probably never going to deal with in this course. In fact, my colleague Professor Vinay Pramod is an expert in handling such sociological problems in a multi-electron system. Okay. So, putting that aside for a moment, what we want to all that we are interested in now in this potential that is seen by the electron which is simply Z effective by A, this effective distance. This gives us a potential and hence a field, right, or Z divided by A square would be the magnitude of the field that is experienced by the electron in here, right. So, now we have a natural scale inherent to the system in the problem for the electric field. Okay, V is Z by A. So, I should be careful. So, now to this entire thing I can set a scale for E. It is often something which we take for granted or is trivial, but it is the most important thing in a scale, the 0 of the scale. What is 0 and what is 1 unit, right. So, if I now plot the electric field in units of Z by say Z effective by A squared, now I can get an idea of the relative strengths, right. The fields that we are often considering are not such gigantic Manhattan structures there. The fields which we usually apply by means of radiation are little Lilliput fields. In fact, this Z effective by A square is called, and we encountered this in the previous lecture once again, this value is called 1 atomic unit of electric field. This is essentially the electric field as seen by an electron in the ground state of the hydrogen atom, the 1s electron in the hydrogen atom, as you might want to call it, right. You can associate an energy with it, that is all fine. We can now do an apples to apples discussion by talking in terms of energies. Okay, this electron is bound to 13.6 eV or minus 13.6 eV below the continuum or the energy with which you supply the system to break it apart, right. But then the fields that we are actually talking about in most scenarios are so small that if I were to put this realistically on the scale, I may barely be able to touch my pen to this scale about the 0, because there is really tiny fractions of this. That is the electric field that the radiation in this visible radiation in this room, which we are using to communicate visually, right, that is of a very small order. You can compute this, right. So, really you need a special source for fields to, I mean, even with the advent and invention of lasers, for a lot of time we were possibly at a tenth, at a hundredth to a tenth of the native field of the atom, if not even smaller. Was it 100 to a tenth? Maybe even much smaller. I should, okay, 10 to the 3, 10 to the 4, because in SI units, the atomic field of the 1s of hydrogen atom is 10 to the 9 volts per centimeter. I am using quasi SI, calling it centimeter. Okay. The fields that you can compute for yourself, the field of a laser beam of say typically 10 milliwatts, which is pretty large for a laboratory scale helium neon laser operating at a wavelength of about 632 nanometers. Just compute the magnitude of E corresponding to this. Remember that this laser can damage our retina if looked into. In fact, we do not even need 10 milliwatts, we can even have a 1 milliwatt and it would be sufficient damage, irreversible damage to our retina. So, it is a substantially damaging field in that sense, right. So, considering that this field, which is it is fairly high for day to day interactions or optical observations, the fields that we apply to matter even with lasers, okay, are seldom going to challenge the might of the native atomic field which is Coulombic in nature. It is the 1 over r field which we are talking about. The moment we start tickling it, okay, to give you an analogy, if this native atomic field were to be an elephant, day to day fields are just the breeze around it. The moment we even touch its tail, which is what we can do with most commonplace lasers, or in fact with substantial lasers, that is when we have any hope of looking at these nonlinear terms to start appearing, to start playing themselves out. Okay. So, which is what we were discussing about in the previous lecture when we looked at harmonic generation. I know this was a bit of a lengthy preamble to some of these things, but this is an important aspect of our discussion. How strong is this field which is strong? So, to observe the second or third harmonic processes, I will give you now some thumb rules, okay, compared to the native fields inside the atom. So, the native atomic electric field E atomic in magnitude is of the order of, you can say, 10 to the 9 volts per centimeter for hydrogen atom, but in other atoms that electron would see some kind of a screen potential, even more so in molecules and condensed matter and so on. So, this field that is seen by the electron is pretty, it could be smaller, but it is of this value. But at what realistic electric intensities of laser beams do I need to consider, or should I need, what is the nominal electric field, or the more than electric field, the intensity of a laser beam do I need to look at second and third order nonlinear effects visibly with a reasonable photodetector, even such as the eye itself. Okay. So, for that, when we talk about lasers, we talk about energy, power and intensity. Seldom do we say, oh, this laser is emitting a light wave with this electric field, because their field is not a really good quantity to, field strength is not a good, or field amplitude is not a good measure, unlike that of a wave in an oscilloscope. In an electromagnetic wave which we read off in an oscilloscope, we often talk about V peak to peak or V RMS. This is really something to do with the voltage or the field that is oscillating in that case. Whereas, in the case of emitted light, we do not talk about the field, we rather talk about the power, the energy or the intensity. Actually, we must ideally speak about intensity, but it so turns out that it is not trivial to measure intensities, it is easier to measure powers for continuous sources. So, we speak about power, and power crossing per unit area is intensity. So, we like to talk about intensities of sources. So, let us convert this electric field into a value of intensity, and I am doing only orders of magnitude in this discussion over here, and I hope to etch these numbers into your minds. So, native atomic electric field, so 1 atomic unit of electric field is of the order of 10 to the 9 volts per centimeter. This translates to intensities of the order of 10 to the 16 watts per squared centimeter, not square meter. Please remember that. A unit of 1 atomic unit of intensity is of the order of 10 to the 16 watts per squared centimeter. Now, therefore, what should be the intensity of my laser? What is the intensity of the laser with which I can have observable nonlinear effects? By observable nonlinear effects, I mean the following. If I take even a weak electric field, okay, a laser pointer which gives me red radiation 700, approximately 600 to 700 nanometers, I shine it through glass, okay. Will I not see the chi2 response or chi3 response, maybe for some reasons chi2 may even be effectively 0 for some media, we will see about that. Now, will I see no, if this is omega, will I see no 2 omega at all, will I see no 3 omega at all? Well, strictly speaking, even with sunlight on falling on a piece of glass, if you filter out the sunlight and take the red, say at 700 nanometers, and shine it on a piece of glass, we should be able to see a violet photon 2 omega at 350 nanometers, second harmonic of 700 being 350. But then the idea is that if you have a detector sensitive enough to capture a single ultraviolet photon at 350 nanometers, right, then it is a different matter. That is not the response that we are talking about, a single photon coming out that you trying to capture, but the kind of response where I can take a detector of a decent dynamic range which can see both the incident radiation and the emitted radiation, such as a nominal photodiode or even the human eye for that matter, to evoke such a substantial response from a medium, right. We need to drive the system with the value of E, which is the driving electric field E. We typically need an E of the order of something like 10 to the 10, it's this, there is no fixed number, but at least something like 10 to the 9, let me say greater than about 10 to the 9 watts per square centimeter. This is of course contingent upon what chi is, what chi2 is. Okay, I would say these are all nominal, for nominal chi2s. Nominal fields are of this type. What do I mean by nominal? Again, adjectives are both a boon and bane in physics, isn't it? So, by nominal I mean if chi1 and chi2 for average, nominal, ordinary, non-extraordinary scenarios, okay, in terms of magnitudes, these have the magnitude, or I should write it like this, the numerical values, the ratio of chi1 by chi2 is nominally again the magnitude of the atomic electric field, which is the ratio is about 10 to the 7, 8, 9. If I have this scenario and I have an electric field, oh sorry, this is not electric field, this is absolute value square of the electric field, should be 10 to the 9 watts per square centimeter. Then I start to excite nonlinear, I start to create the scenario wherein the displacement of the electron cloud, okay, makes excursions into region beyond the linear response region. Take home messages and numbers, native atomic fields are about 10 to the 8 to 9 volts per centimeter. Convert this to intensities, 10 to the 15 to 16 watts per centimeter square. To have a reasonable nonlinear response, we need fields which with light sources with intensities in excess of about 10 to the 9 watts per centimeter square. However, tomorrow if you find a medium where you start exciting nonlinear response at much lower values of intensity, say 10 to the 5 watts per square centimeter or 10 to the 4 watts per square centimeter, typical helium neon laser, okay. don't slap that on me, you will be able to see it. Why? Because there are of course nice media, exotic guys for which this is not always valid. Chi 2 can be extraordinarily large compared to Chi 1. Okay. So, a surprising candidate for that, is the medium rhodopsin. Rhodopsin is the pigment in the retina that helps us to have vision. But of course, we can grow this on bacteria. So, there is such a medium as bacteriorhodopsin, or we can induce some thermal effects in media. So, we have thermal response in media which can also lead to nonlinear behavior. Those thermal responses actually it's a cumulative response over time in the medium. You start to heat up the medium and modify the refractive index. So, there is such a thing called the thermo-optic effect. The refractive index of a medium depends on temperature. So, you keep passing a laser beam through a medium, you locally heat it. So, the leading parts of the beam heated the medium where the lagging regions come and interact, and that is also a nonlinear effect, right. The harder you shine the light, the greater the refractive index modulation, and you have so called thermo-optic or thermal response of the medium, which can also lead to a nonlinear behavior. Okay. So, modulo these kind of scenarios, you need nominally a high a relatively strong electric field to have observable nonlinear effects. If we have such fields,